Hi, my name is Oliver Taradash, and for this physics project, I'm going to show how a camera flash uses a capacitor and a resistor to store and release electrical energy. A flash is extremely bright, but only for a fraction of a second, and then that's because the capacitor dumps all its stored energy very quickly. When you take a picture with flash, the camera charges up a capacitor to a high voltage. Once it's charged, the capacitor discharges almost instantly through the flash lamp or LED. That quick release of electrical energy is what gives you that bright pulse of light. Inside the circuit, there's a resistor that limits the charging current, so the capacitor charges gradually instead of instantly. The charging behavior follows an exponential curve defined by the time constant. Okay, so for the physics, we're only going to be looking at this part right here. The physics behind this capacitor energy storage and RC charging. A capacitor stores energy in an electrical field and is stored in this equation given. So for U is the energy stored in capacitor as joules. 1/2 is the constant, C is the capacitance, and V is the voltage. The reason I chose 10 joules of flash energy is because real cameras, like disposable cameras, typically release 5 to 20 joules of light energy in a single flash. And why I use 300 volts? Camera flashes do not operate at low voltages like 5 to 12. They charge the capacitor to 200 to 330 volts before charging it through the flash lamp. And once I put it into the equation, I get 2.2 times 10 to the negative 4, which is the capacitor's 220 microfarads. Now let's see how long it takes to charge. Say the charging resistor is 1.0 ohms. The time constant is T equals RC, and T equals 1,000, and then the 2.22 times 10 to the negative 4 equals the 0.22 seconds. That means after about one time constant, the capacitor is 63% charged. Cameras usually wait about 3 to 5 time constants, so the total charge time is around 1 to 1.2 seconds. When the capacitor is empty, the initial charging current is this. And so then we have the 300 divided by 1,000 equals 0.30 A. So the flash circuits start with 0.3 amp current, but it quickly drops as the capacitor charges. Now I want to show you how to connect this to something we actually use every day, as like my camera flash. When I turn the flash on and take a picture, the phone's internal circuit has to charge up a capacitor first. Sometimes you'll notice a slight delay or a little flash icon charging. That's literally the capacitor being charged to a high voltage. Now I'm going to take a picture and notice the flash. In that instant, the capacitor we talked about dumps its stored energy into the LED. The energy stored is what I calculated earlier using the U equals 1/2 CV squared. If all gets released in a fraction of a second, which is why the flash is so bright. And now if I take a few photos in a row, sometimes the flash needs a moment to recover. That's the RC charging happening again. The capacitor has to recharge through a resistor before it can fire full brightness. It's a little delay. So in this project, I demonstrated how a capacitor stores the energy needed for a camera flash and how a resistor controls the charging speed. I calculated the capacitance needed for a typical flash, the charging time constant, and the initial charging current. This is a simple but easy way to show how RC circuits are used in real electronics. Thank you for watching.